Peilin, and my project is about Epsilon scheduling as an improvement to deep Q learning. And so before introducing to the algorithm of deep Q learning, we have to talk about reinforcement learning. So reinforcement learning is an unsupervised machine learning algorithm that seeks to learn the optimal behavior in an environment that maximizes the reward obtained. For instance, in a game environment where machine learning algorithms are usually tested in, the reward might be opening a chest in a room, or having a longer survival time, or even to killing an enemy. So being unsupervised, the AI agent must independently explore and discover the set of actions that maximizes the reward through the process of trial and error, which is interesting as it's very similar to how humans learn. And the agent approaches the trial and error through a sequence of observations, actions, and rewards. And the reinforcement learning algorithm can be modeled through the Bellman equation here, which seeks to find a set of actions that maximizes the cumulative reward in state S and takes in action A. So as we can see in the Q star function here, the Q star function is called the value function, which records the accumulated reward, while the R function is the reward function, which returns the reward on when the agent taken action A in state S, and the gamma is the discount factor, which denotes the significance of past actions taken. So once we have learned the Q star function, we can then obtain our policy, which is the pi function here. So this is how the Bellman equation obtain the optimal policy. And so basically, deep Q learning, and DQN is short for that, it combines the reinforcement learning with a class of neural networks known as the deep neural networks. So deep Q learning selects the actions that maximizes the future rewards, similar to how reinforcement learning works, through using deep neural networks to approximate the action value function, because in some cases the action spaces might be especially large that it takes a lot of time to compute with simply reinforcement learning. So the parameters of neural networks will be updated periodically in order to balance learning and stability. And the equation below models the loss function of the DQN that we seeks to minimize over the learning process. Okay, so moving on, here's the illustration of neural networks where there are multiple convolutional layers. So given observation, the neural networks can successfully return actions being taken. So for Atari games, we have the controllers turn into different directions, and also button. And while DQN is certainly an innovative algorithm that improves the performance, that improves upon reinforcement learning, there are also certain issues with DQN and corresponding extensions that seeks to solve those problems. For example, there are double Q learning, which reduces the overestimation error through using two neural networks for selecting the optimal actions and evaluating. And there's also the prioritized replay, where this extension will adjust the data distribution, where the more informative and favorable transitions are sampled more frequently, which improves the efficiency of the learning process. And next we got noisiness, which improves the exploration of the data through ignoring the noisy streams during learning. And the noisy stream is very detrimental to deep Q learning, as it can um, significantly impact the actions that the agent take, while the noisy streams does not play a significant role in the game itself. And my focus is on the exploration and exploitation process. So exploration is where the agent takes a random action, and exploitation is where the agent chooses the optimal action learned. And so and often so there are different ways of exploration and exploitation, and often we conducted in the epsilon through the epsilon greedy policy, where we'll take an random exploration with the probability of epsilon, and we'll take the optimal action learned with a probability of 1 minus epsilon correspondingly. And the epsilon will they're usually modeled through a linear decay. And so my idea is simply we can model the decay of epsilon through uh, other methods, such as quadratic or inverse function, or even sine and cosine waves. So my goal is to modify the epsilon schedule uh, and to explore beyond the linear decay of epsilon. Oh, just to mention, the linear decay, the reason that epsilon is decaying is that we want to have more exploration at the start of the learning process, because the agent will like to. It's better if the agent learn like what actions can be taken, and then we have less exploration and more exploitation as we move on to the learning, because the agent has already accumulated experience in selecting optimal actions. So this is why the epsilon, which denotes the probability of taking a random action, should decay over the learning process. And so here is the linear decay of the epsilon. So the left on the left, the diagram denotes the decay function, while on the right is when the function is differentiated, so it denotes the rate of change of the epsilon value. So for linear, the rate of change of epsilon is constant. So the probability of taking a random action, which is simply exploration, will decrease uniformly over time. So this is how we usually model epsilon. So moving on to other methods such as quadratic, we can see that the epsilon on the left diagram, epsilon decreases less at the start of the learning process, which actually grants us more exploration at the start. And we also have the inverse function. While the diagram on the left might not be a very precise precise illustration, because the epsilon usually starts the value of epsilon usually starts at 1, because or value close to 1, because 1 is the one is the highest probability. So we can see that in the inverse function, if you model epsilon through an inverse function, the exploration decreases significantly at the start of the learning process, while the decrease tends to be more to get more flatter. So there's less of decrease in epsilon as we move further into the learning process. And we also have the exponential decay, where also the decay of epsilon will tend to get smoother as we move deeper into the move further into the learning, and it decreases more rapidly at the start of the learning process. And the one that I really like is sine and cosine waves, where the exploration will tend to decrease less at the start, and it will get smoother in the middle of the learning process, and at the very end it will actually it will also get smoother. So this is I hypothesize that this will be one of the optimal ways of scheduling epsilon. And another one idea that I got is to use adaptive scheduling, where the epsilon will decrease, on which there will be a decrease of acceleration, where the reward is increasing because the optimal policy that have been already learned is helping the agent to increase its performance. While if the while if the rewards are plateau and they are not changing much, we'll have an increase of acceleration, which means an increase of epsilon. So, so in my opinion, adaptive scheduling and the sine wave scheduling is the most comprehensive way to schedule epsilon and may lead to better performance because it grants more exploration when needed and more exploitation when needed at the very end of the learning process. However, I'm also aware that the epsilon schedule itself might be a trivial improvement to the deep Q learning itself. So in order to test how the performance of the different epsilon scheduling methods, I will first implement the methods on the simple control problems such as cartpole, and then I will move on to implement the different scheduling methods on Atari games in order to evaluate the comprehensive performance of the the epsilon scheduling methods on different environments. So even though it is the project is still ongoing, I would like to acknowledge my supervisor Garrett and my for providing me invaluable advices and guidance throughout the project. And I also like to give special thanks to my parents and friends for their continuous support and understanding. And so this is my current progress and thoughts on my project. And thank you for listening.